Today we're learning about equilibrium and calculations with equilibrium. So you already saw a demonstration of some magnesium hydroxide dissolving just a little bit. So that should look like starting at zero concentration of ions, rising a little bit, but then leveling off as the reverse reaction starts to equal the rate of the forward reaction. So when it levels off, that's called a steady state, or you've reached equilibrium. So you can find that concentration, and that would be the concentration of at equilibrium. It's when it levels off. So an equilibrium constant is just a ratio of products to reactants at equilibrium. The symbol is capital K, big K. So at equilibrium, if K is large, that means products is more than reactants because it's calculated products over reactants. If another way of saying that is that it's product favored. You calculate K by the concentration of the products raised to its coefficient, or the reactants raised to their coefficient. So remember, brackets mean concentrations. So we're going to do all the products. So that's going to be ammonium and hydroxide for this example, over all the concentrations of reactants, which is just ammonia here, because water doesn't have a concentration because it's a pure substance. So if in an equation something says liquid L or S for solid, then you don't put it in the equilibrium expression because it doesn't have a concentration. If it says G for gas, it does have a concentration because it's dissolved in air or in a container. So tip, do not include pure solids or liquids. Here's another example. Write the equilibrium expression for the milk of magnesia reaction you just saw. So sometimes in this equation the water is written over the arrow. I'm writing it on both sides so we can practice leaving it out. So we're going to have both products raised to their coefficients. You don't have to put a 1 here, I'm putting it to emphasize that it came from the coefficient, which is 1, over the reactants. If we look at the reactants, this says L, it's a pure liquid. This says S, so it doesn't have a concentration either, so there's nothing on the bottom here. You can put 1 if you want. Okay, so equilibrium constants can be written for stepwise reactions that react in a series of steps. You can figure out the overall equilibrium constant from those. And if you have a reaction and you want the equilibrium constant for the reverse reaction, you can also figure that out. So if we had a reaction like reactant A forms C and D and then C forms E and D, overall that's A forms E plus 2D. If I knew both equilibrium constants, 1000 for the first one, 0.5 for the second one, why don't you pause and think, how could you calculate the overall? So the first reaction is products over reactant. Same for the second reaction. Now the one we're trying to get overall is for the overall equation, products over reactant. So if you look at it, what are we doing with K1 and K2 to get those? You should be able to see that C needs to cancel out and D is being multiplied by each other, so they're being multiplied. So if you have to add up reactions, it's basically making more products and more reactants, so you have to multiply the equilibrium constants. Okay, so if we have to reverse an equation, for example, A plus B forms C if K is 2, I would define K for C forms A plus B. So if we are reversing the equation, then we are making the products reactants and making the reactants the products. So we are flipping the equilibrium constant expression. Expression just means math equation for calculating the equilibrium constant. So if we flip the expression, the math equation, that means we need to flip the value also. So invert it, do 1 over, I guess it's inverse. So K would be 1 over 2. And then if we were doubling that whole equation, then we're doubling the coefficients there, so we need to square everything. Because equilibrium constant is products or reactants raised to their coefficients. So if we're squaring everything, we would also square the value. So if you multiply a equation by a coefficient and you wanted the new equilibrium constant, then you would raise the old equilibrium constant to that power. So that'd be 2 squared, or 4. So finally, how would adding a catalyst or changing temperature change the equilibrium constant? So adding a catalyst increases the rate of the forward and reverse reaction because it just lowers the activation energy. It doesn't affect one more than the other, so it does not change the equilibrium constant. Changing temperature is the only thing that does change equilibrium constant. And whether it makes it bigger or smaller depends on whether the reaction's endothermic or exothermic. Endothermic reactions need energy for the forward reaction, so that increases the forward reaction and makes K bigger. Exothermic reactions would need energy, use energy for the reverse reactions, so that would make K smaller if you increase the temperature. So here's a diagram that shows you about the catalyst. Catalysts lower the activation energy by the same amount for the forward and the reverse reaction. So overall, there would be no effect. So K does not change. Changing temperature, it would increase the rate in the one direction more than the other. If you have a higher temperature, it will make everything in that reaction collide more because there's more motion of reactants and products, but increases the rate of the reaction that uses energy more. So it does change the equilibrium position. If it's an endothermic reaction, then increasing temperature would make K bigger. If it's an exothermic reaction, then increasing temperature would make K smaller.